Hi, this is Jeff Heaton. Welcome to Applications of Deep Neural Networks with Washington University. In this part, we're going to look at how to use a deep Q neural network. So a deep reinforcement neural network that allows the computer to learn to play a game. We're going to start with a relatively simple example. We're going to see pull cart using TF agents. And we'll then, in the next part, expand this to be more complex. We'll use an Atari game. And then following that still, we will actually create sort of a financial simulation. So do something that's not even a video game. To see all my videos about Kaggle, neural networks, and other AI topics, click the subscribe button and the bell next to it and select all to be notified of every new video. Okay, now we're going to look at Q-learning using the OpenAI gem. We're going to use Keras to do it this time, so we're going to use TF agents. So we're actually using deep neural networks now to build up that Q table that you saw before. So essentially in Q-learning, you build up a table that has a list of every possible state the world can be in, and then the anticipated rewards of your next steps. Now, I am going to run this in Colab because a GPU is useful for this. I am going to go ahead and choose runtime and run all because at least with the current version of this, hopefully this improves by the time that you run this, you'll get an error actually going through this with the current version 2.2 of TensorFlow and some of the other things that they have installed in Google Colab. So see, it's running. This part of the program here that just gets me the right version of TensorFlow that I want. This part here is doing some installs to put various software in that we need, like TF agents. And this other software lets me just capture the game being played as a video so that I can play it in Colab. You can use this on your own if you're running locally on your computer, or you can leave this part out and it'll just pop up a window and show you how the game is being played. Okay, so this is where you normally get this error. And I wanted to explain this to you because this only started happening a few days ago when Google upgraded some stuff in Colab and TF agents as well. And if you get this error, basically, and let me explain one other thing too. If you get an error like this error is not telling me a great deal. If you Google this, they're going to basically just say to reinstall protobuf, which is actually not what it takes. So this took me about an hour. And the way I figured this out was basically by going up here and running each of these in part and then seeing which of them was actually causing the error. And when I ran it separately, I actually got to the error that was really happening. And it was basically saying that since I installed all those packages above there, I need to restart my runtime, which I'm doing now. And now I can basically do a runtime and run all. And it'll make it through there just fine. It's a little trick there. You might not need to do this. If you don't get the error, don't worry about it. They fixed it since I recorded this video. Now, while this is running, because this takes a little while, and notice too, even though I restarted the environment, it's saying already newest version. That was from my last install of this. So if I go away from this for a few hours and Colab times out and takes my environment away, then I've got to rerun it from scratch. But even though I restarted the environment, my changes to the hard drive by installing these was still the same. So that is kind of how that works. Now, this should have made it through the part that was erroring before. Certainly hope so. Between Google Colab and TensorFlow, they like to send me back to the drawing board a lot. But that's part of what I do as far as making these videos, is showing you how all this stuff works together. And believe me, machine learning changes at the speed of light. Code that I had working a week ago may or may not still be working. So that's why always make sure that you check my GitHub repository to get the latest version of these things. So as we go through all of this code that I'll be explaining in a moment, good. It's training, so it has made it completely through. So I'm going to let it go ahead and train and run while I explain sort of what's going on here. These are all of the imports that you need. Just go ahead and use those. These are the hyperparameters. Some of these are important. Some of them not so much. Number of iterations is very important. This is how long you're going to train. You're not really using early stopping in this capacity. You're simply picking the number of iterations. I did not set up this so that it's restartable. That might be a very good modification to make for this, because if you're doing something really complex, you may train it for 20,000 epochs and then realize, I want to train it for 20,000 more. This is very important. This will define the success or failure of your project. You need enough iterations. Initial collect steps. This is not that important. At least I've not found it to be. This is how many times you run through episodes to get some initial data to train your neural network with. Collection steps per iteration. This is actually very important. For a simple one like this, I set it to 1, but you might want to set this on the Atari. I think I set this to about 10. It takes it a lot longer to train, but you get much, much better results typically. Collect steps per iteration and iterations itself really is the only downside of increasing those is going to make it's just going to take a long time to run and to train. I wouldn't set this too far above 10. I set it usually somewhere between 1 and 10. This is the size of your buffer. So essentially it's running through episodes and it's storing information from each game that it plays. Initially it fills 1,000 of them before it starts. This is just how many steps you're really willing to store in there. This is the batch size, which is pretty typical for machine learning. You might get better results with a little smaller. So your learning rate, this is absolutely critical. I typically spend most of my time tuning the learning rate, the collections per iteration, and the number of iterations. Basically, you want this number as big as possible. If you set it too big, then it's going to become unstable very quickly. 10 to the negative third works really pretty well for this. But if you find you're not stabilizing, change this to -4, -5, so on and so forth. But the bigger you make it, like a -3 or -2, you probably won't get by with. But in that range, it's going to train faster. It'll need fewer iterations. This is how often we want a log report. And this won't affect your training much, but it lets you know what's going on. The number of evaluation episodes. So how many episodes, how many complete runs of the game do you want your evaluation based on? 10's a good number. And then how often do you want to evaluate? Don't set this too low because it does take time to do these evaluations. We'll see in the Atari game, I let it go much, much further before doing evaluations, just to keep things efficient. The environment that we're going to use CartPole. That is where it's basically trying to move a cart that has a pole balanced on it, and you don't want the pole to fall over. So basically figuring out gravity and angular momentum sort of thing. I like this code here. This lets you render what the environment looks like, so that's a great way to visualize it. There's the cart, there's the pole. The pole is connected by a hinge to the cart. And I print out some basic data on it so you can see that the observation, there's basically 4 values being observed, which is basically the velocity of the cart, the angle of the pole, and the angular velocity of the pole. And also the position of the pole. That makes of the whole cart. That makes the 4th one. The reward is pretty simple. It's just a number value based on how long you've kept the pole upright. And this describes sort of the values that are being kept. Let's see. I'll go ahead and mention this too. You'll see that we deal with TF-Pi environment and TF TensorFlow environment. There's 2 environment types that you can deal with. Usually you're dealing with Python environments, but TensorFlow environments are written completely in TensorFlow. So that means you can literally compile that along with the entire execution tree of the neural network, and they become very, very performant. However, usually, or at least in this case, the Atari games, all these things are written in Python, or at least written in languages other than TensorFlow, so we almost have to use the Python environment. I found myself usually using the Python environment. I've not used the TensorFlow environments a lot. I bet you could get considerably faster access there. Although sometimes I just prefer to throw compute at it, because the more stuff that I program that is TensorFlow specific, if I ever want to try something else like a PyTorch and swap it out, there's more legacy sort of stuff tied to one particular platform. Doing it in Python lets me stay pretty agnostic. So just a few design considerations here. The agent. We're going to use a DQN for this one. DQN is great when your action space is Boolean or is discrete. So you either, in this case, you're either applying force in one direction or the other, left or right, true or false. It's not how much force. If you do need to have a continuous or a numeric action space, then I recommend DDPG. That is the one that we will be seeing, not next part, but in the 5th part for this module, because that lets us have continuous action space. And for the financial simulation that I'm running, I want continuous. I want it to be able to tell me what % of income should be invested in a particular direction. So the agent, we create the Q network. The Q network is the underlying deep neural network, and then we place the Q network into the DQN network. Most of this code for your own use, you can just take it in this form. It's adjusting to what the environment says the action and observation space is. The policies, this is used inside of the agent to determine what you're going to do next. We're going to use a random policy here so that we are able to fill that initial buffer with values so that the neural network can start training. Metrics and evaluation. I like this compute average return. I got it from the TF agent examples, but this basically is looking at what was the reward return coming from the episode as it played out and summing that up. So this is a function, really, this entire CartPole example comes from the TF agent's examples, and then I expand it to play an Atari game in the next part. But this is basically just looking at what was our average return over a number of episodes, in this case 10. I find this to be a good way to measure this because the world that the agent is operating in is stochastic. So there is some randomness going on there. So each of these episode runs are not going to be the same. And the average that it gets with those randomness gives you an idea of how good it's performing. And you can see with this comment here that was in the TF agents example, TF agents does have a number of built-in metrics that you can use. And I definitely encourage you to take a look at those. We compute the average return for the random policy, just showing that it works. The replay buffer, this is very important, is fundamentally you're training a neural network through all of this. And this lets you store the data that you're training the neural network on. Because the way the neural network is actually working is you have a state. And that state in old school Q learning, every possibility of the state can result in some action. And we simply train the neural network for each of these actions that you might have, predict what the Q value is, what the possible reward is. So you feed the neural network in the state, and it returns to you all the rewards of the action. Now this is using a table, so the problem with the table is you have to have a row for every single possible state, and you just look it up and you find it. Now with a neural network, the state is going into the input neurons, and then the neural network, through neural network magic, predicts for you which action you should take. So it gives you the Q values of all your possible actions, and whichever action has the highest estimated Q value, you're going to use that one typically as your action that you're going to choose. Now, neural networks need to be trained, so that's what that replay buffer is for. As you run through episodes, you take all of these states and you put it through here, and you see what your reward actually was. And that becomes the replay buffer, the training data. Because you're going to actually see what the rewards were from what the neural network did, and that adds additional rows in, so the neural network helps you get up to a certain state, but then that next state, you let the neural neural network tell you what to do, but then the reward, you train the neural network based on that reward so that it can predict what next step it should have taken. So it's constantly getting that reinforcement. The neural network is helping you get to these states further and further into the game, but then you feed the reward actually from the video game. Did you score a point or did you get killed? That all has to factor into those Q values. And that's what you're teaching the neural network to do, because this works better than having a table. You can't have a table for every possible combination. The neural network learns to generalize this theoretical, gigantic, high-dimensional table and basically predict for you those Q values. Data collection. This is where you're generating those 1,000 steps so that you get a random set of data. So what we're basically doing, we have a collect step that is being called by the main function collect data. And this is right from the example in TF agents. What we're doing is we're calculating the time step, so how far we want to project. We're taking the action over that time step, and then we are getting all the data from that step and the trajectory that it used to get to the next step, so the action, and adding that into the training batch. And that is how we're slowly building one by one these rows that the neural network is actually learning to train on. Then we go through the number of requested steps. This is actually a bug I found in the TF agents code. I left it exactly like this, but they do have a hyperparameter up higher where they let you specify the number of steps, and down here they ignore it and just do 100. I fixed that actually in the Atari example in the next one because that becomes important. And then we convert this into a data set and we're basically ready to go. Now we're training the agent. I kicked this off earlier. Unfortunately, it finished, so that is good. We are basically going through a loop here with some setup, the number of iterations that we want to step it through. So that's the 20,000 from up higher. It's one by one continuing to build the data set that we have so that we continue to train the neural network on it based on the rewards that we're actually seeing. If we reach the log interval that we wanted, then we go ahead and print out some progress information. If we've hit the evaluation interval, then we evaluate it using that average return function that I showed you earlier. And here you can see, as it's training, the average return tends to increase as it goes. I think 200 is the maximum it can get. Now, to see it actually run, we've got the video code. We've seen this before, so it increases, gets to just about its maximum and stops. If you want to see it actually work, you can see it is balancing that pole really quite well and yet moving it across the field of view. It's harder than it looks. If you try to run this with just the random one, it dies quite rapidly. Once that center of gravity is gone, it stops because it's going to fall. There's no reason to continue. All right, that is a basic introduction into Q-learning. Thank you for watching my video. In the next part, we're going to see how to apply the same technique to an Atari game. If you're interested in this sort of thing, please subscribe to my channel. Thank you very much.